When an electrical current flows through a conducting material like iron, copper and aluminum, it flows as a drift of free electrons in the metal which can move freely around in the object. It results in the flow of current through the circuit. However, if the conductor is replaced by a dielectric material such as plastic, glass or ceramic, the current doesn't flow. Dielectric materials are a poor conductor of electricity. Unlike the conductors, they have no free charges as all the electrons are bound and associated with the nearest atom. The polar molecules in the material are in a random alignment. However, they are efficient supporter of electrostatic field. On the application of an electric field, the dipole moments of the polar molecules align inside the material. The positive charges within the material are slightly shifted in the direction of electric field and the negative charges in the direction opposing the direction of electric field. This results in the polarization of dielectric materials. Dielectric material find its use in energy storage application like capacitors to increase the effective capacitance. It reduces the electric field strength between the capacitor plates, and also reduce the possibility of shorting out by sparking during high voltages. These materials are also an essential element of a transformer where it is used as layer-to-layer insulating materials of the transformer windings. Polyvinylidene fluoride polymer, commonly known as PVDF, is a dielectric. It is flexible, inexpensive, lightweight and has high Curie temperature and breakdown strength. It is used for energy transfer, generation and storage and is commonly used in capacitors, sensors and actuators. However, it suffers from a low dielectric constant. Diisopropyl ammonium bromide dipob is a molecular, ferroelectric crystal with high spontaneous polarization. It is ionic crystal which is easy to synthesis, inexpensive, high melting temperature and high breakdown strength. Dipob has high dielectric constant of 88. The properties of the material change at the nanoscale. PVDF finds its use in flexible nanoelectronics, however, low dielectric constant limits its usage. PVDF dipob nanocomposite thin films have previously shown enhanced dielectric strength and a good chemical stability. Electrospinning is a technique which uses electric force to produce ultrafine nanofibers. Dipob-based PVDF nanocomposites in the form of thin films have previously shown enhanced dielectric strength and a good chemical stability. We have used electrospinning setup to create unique 2D nanofibers where the dipob nanocrystals grew in situ during PVDF nanofibers formation. The X-ray diffraction analysis confirmed the presence of both PVDF and dipob materials. Infrared spectroscopy further confirmed the presence of the dominant dielectric phases in both the structures. Scanning electron microscopy displayed a good alignment and size distributions in dipob-doped PVDF nanofibers. Transmission electron microscopy further confirmed equal distribution of dipob nanocrystals in the fibers which grew in situ during electrospinning process. The frequency-dependent analysis conducted on the electrospun nanocomposite fibers showed an enhanced dielectric constant. Dipob concentration-based tunable dielectric constants were observed in the nanocomposite samples. The measurements performed along the length as well as perpendicular to the length of nanofibers confirmed the alignment of dipoles in uniaxial direction. Due to the large difference in the electrical conductivities of PVDF and dipob, the charges can migrate and accumulate at the interface of the materials. This results in interfacial polarization, and hence a relatively high dielectric constant. The dielectric constant was also affected positively when dipob was added to PVDF because of the highly ionic nature of the dipob crystals that contributed to the dielectric constant by ionic polarization. Electrospinning at high voltages resulted in pooling in PVDF structure, where the alignment of the dipoles is along the length of nanofibers. It caused an increase in the effective dipole moment as a result of orientation polarization.